All right, let's go ahead and talk about these problems. So one thing to know about integrals, antiderivatives, area under a curve, all these things is there's often more than one way of calculating a thing. Specifically, some areas under curves, we can just use geometry formulas we already know. This region here is a parallelogram, but we can definitely use triangles to calculate its area by seeing that it's kind of a larger triangle that starts at -3 and goes up here like that. This point's 5, 16, minus the area of that smaller triangle that starts at -3 and goes over to 1. Right, if we do that bigger triangle minus the smaller triangle here, we can totally find the area. This bigger triangle, well, has a base of -3 to 5 is 8. So it's 1/2 base, which is 8, times the height, which is 16. And the smaller triangle has a base of from -3 to 1 is 4. So the area here is going to be 1/2 times the base, which is 4, times the height, which is 8. So we end up getting, let's see, 1/2 of 16 is 16. So that's going to be 8 times 8, which is 64, minus 1/2 of 8 is 4. So that's going to be 4 times 4, which is 16. So the area of this parallelogram, or the area under this curve from 1 to 5, is going to be 64 minus 16, which is 48. So this integral from 1 to 5 of 2x plus 6 dx is definitely equal to 48. One way we can find the area. And the reason we're finding it that way is so that we can see that when we do it the other way using the limit definition, we're going to end up getting the same answer. Unless I made a terrible error somewhere. So definitely make sure you pay attention, right? Sometimes they make mistakes. Call me out, be like, hey James, you mean, like, I'm not offended. I know I'm a human being, I make mistakes occasionally. But let's do the other thing where we're going to use the limit definition to calculate the area. So if we want to find, got some paper here, this limit here, and again, I'm going to use right endpoints. So when I start thinking about doing this, I really like to draw my region. So I've got my function. I'm going from 1 to 5. And I'm really thinking about just breaking this up into, well, my delta x is going to be b minus a over n, which is 5 minus 1 over n, which is just 4 over n. So each subsequent endpoint is just 4 over n further to the right. So this first spot here is 1 plus 4 over n. This next one is 1 plus 2 times 4 over n. And it just keeps on going. So you get to the one over here that's like at the kth spot. This is one's going to be 1 plus k times 4 over n. You guys can see that all right. So my x sub k, which I'm using as my right endpoint, is going to be 1 plus k times 4 over n. And that's what's going into this limit of the sum of f of c sub k. And I did write c sub k here on purpose because although xk is the right endpoint, we're choosing the point we're using to be the right endpoint. This is a little nitpicky. I wouldn't worry too much about this really, depending, I should say, it all depends on who your teacher is. Some people care a whole lot more about this than other people. Some people are like getting really into the details and we're like, yeah, we've never even talked about this. So it can really depend on who's teaching your class, how much of this you're going to see. The idea here is we can then take, this is our c sub k, this is our delta x, and write that the integral from 1 to 5 of 2x plus 6 dx, which again just means the area under the curve, 2x plus 6 between 1 and 5. That's all that notation means. That's equal to the limit as n goes to infinity of the sum from k equals 1 to n, of f of 1 plus k times 4 over n times 4 over n. And then we're going to use our function that is f of x equal to 2x plus 6 to replace this part here with 2 times what's being input there plus 6. So when we rewrite this, it's going to become the limit as n goes to infinity of the sum from k equals 1 to n of 2 times 1 plus k times 4 over n plus 6 all times 4 over n. So the questions about what we've done so far. We're using this particular this particular version of the limit definition to actually calculate the limit of the Riemann sum. So we're adding all the areas of the rectangles together and then letting the number of rectangles get more and more and more, so their width gets narrower and narrower. And then it's kind of a formulaic process. We multiply this out, we break it apart, we use the formulas that we talked about last class. So multiplying this out, it's a little messy, but not too terrible. The limit is n goes to infinity of the sum from k equals 1 to n. Let's see. 2 times 1 is 2. 2 times 4k over n is 8k over n plus 6 all times 4 over n. 2 plus 6 is 8. So that's going to be the limit that then goes to infinity of the sum from k equals 1 to n. 8 times 4 over n is 32 over n. And 8k over n times 4 over n is 32k over n squared. This is where I always pause and ask myself, in each of my fractions, is the power of n 1 larger than the power of k? Yes, I got n squared and k to the first, I got n to the first and k to the 0. That's a good sign. It means I'm on the right track. So we're going to break this up. We're going to write as the limit as n goes to infinity of 32 over n times the sum from k equals 1 to n of 1 plus 32 over n squared times the sum from k equals 1 to n of k. Can you explain one more time how you got the 1 plus k times 4 over n? Yes. So the way I'm doing that is I'm seeing that if I'm in my first subinterval, the right endpoint is 1 plus 4 over n. And in my second subinterval, I've moved another 4 over n over. In fact, let's zoom in really close here. So this length right here, that's 4 over n, because that's my delta x, how wide each subinterval is. This is also a 4 over n. Sorry, that's, oh, I labeled the wrong one there. Sorry. That's a 4 over n. That's a 4 over n. So I've added 4 over n twice. If I want to go to my third subinterval, then I add another 4 over n, and 1 plus 2 times 4 over n plus another 4 over n is 1 plus 3 times 4 over n. So we can see that for the first, second, and third subinterval, the first one is 1 plus 1 times 4 over n. The second right endpoint is 1 plus 2 times 4 over n. The third endpoint is 1 plus 3 times 4 over n. And if we go out to the kth subinterval, we've essentially just gone over 4 over n k times. So we've added 4 over n k times, which is the same as k times 4 over n. So that's how we're getting 1 plus k times 4 over n. One nice thing to see with this is you can check to see if you're right. If you think your formula might be off, give yourself a little check. The left-hand endpoint should be your x sub 0. So if I plug in 0 for k, x sub 0 should equal 1 plus 0 times 4 over n, which is 1. Okay, that checks out. And my right-hand endpoint, which is 5, should be your nth right-hand endpoint. Right, this is your nth subinterval, and the right endpoint is x sub n, the left endpoint is x sub n minus 1. If you plug in n, x sub n is going to be 1 plus n times 4 over n. Sorry, you can't see that. Apologies. I know I zoomed way in. But n times 4 over n, the n's cancel, and you get 1 plus 4, which is 5. And that checks out. So your x sub 0 should always be your a value, your lower limit, and your x sub n should always be your b value, your upper limit. If you're not sure if it's right, you can check. Yeah.
At the end where you just left off, how come you were able to take out 32 over n from the summation function?
Excellent question. So as far as the summation is concerned, the thing that's changing is k. K is increasing from 1 to 2 to 3 to 4 to 5 to 6 to all the way to whatever n is. But we're pretending like we don't look at that limit. As far as that sum is concerned, n is just some constant. It could be 1,000. So we're saying, oh, n is like 1,000, and we can totally pull out a constant 32 over 1,000, or a constant 32 over 1,000 squared. So it's totally fine to pull out anything that's not your index from a summation. They all act like constants as far as this summation is concerned. I know it's always a little tricky because the n feels like it's a variable thing that should stay in there, and it kind of is, but not as far as the sigma is concerned. Hopefully that answered your question as well, Alyssa. So then once we get to this stage where we've broken it into its pieces that are different summations and we pulled out any constants, now we have to use those formulas. So we have to remind ourselves that, well, the first one's fairly straightforward. The sum from k equals 1 to n of 1, you're adding up 1 n times and you just get n. And then we have 32 over n squared times the sum from k equals 1 to n of k. We saw last time was the formula n times n plus 1 over 2. And if that doesn't look familiar to you, or you're curious about why that is the way, I would encourage you to go back and look at the class from last Friday, which is on Canvas. Okay, you have a question, Manny? No? Okay, cool. So then at this point is where I would encourage you all not to do much more writing. Personally, I would say, okay, 32 over n times n, those just cancel. You get 32. And the limit of this, if we look at this, this looks like, okay, I'm going to actually multiply it out just so you can see it. But what I really care about is if I multiply this out, this is n squared plus n. All times 32 is 32n squared plus, I don't actually care about the smaller terms. I know it's 32n, but we don't care. We only care about that first term over 2n squared. And so the limit of that as n goes to infinity is just 32 divided by 2, the quotient of the leading coefficients. Just like it was back when we talked about limits to infinity in 21a. So that's going to be 32 divided by 2, which is 32 plus 16, which is 48, just like we already got when we did it the other way. So of course, when you're calculating something, it shouldn't matter how you calculate it, you should get the same answer. But it's nice to see that whether we do this using geometric knowledge or do it using this limit definition of the integral formula, we can get the same answer. Cool. All right, so let me poll the people in class and on Zoom. How many of you are seeing this kind of work in your class? And no one? Oh, you? Okay. Anyone on Zoom seeing this in class? Okay. How many of you can raise your hands or start writing in the chat, have started talking about the fundamental theorem of calculus or have gotten past it already? Okay, a couple of you. All right, all right. It's always fun with on-quarter classes because there's like 6 or 7 different 21B classes and everyone's like, let's do way different things. So let's do a couple more examples of this and then we will move on a little bit. Let's use the limit definition again. So we want to use the limit definition, calculate the area under the curve, 6x squared plus x over the interval from -2 to 3. Or in other words, integral from -2 to 3 of 6x squared plus x dx. Now, no, I don't want that. Let's just do it. So whenever I see use limit definition, I'm thinking, all right, that's going to be the limit as n goes to infinity of the sum. I like k, you can use I or j or whatever. And k equals 1 to n. Oh yeah, question.
So last time on Friday when I was watching the video, I noticed that the norm of the
Right.
partitions
Yes.
goes to 0.
Right.
Why are we using as n goes to
So here's the deal. And that's a really excellent question. So when we talk about a partition, if we go from -2 to 3, we are using, usually, if we're just doing kind of the standard boring way, a regular partition. regular partition. The partition P consists of all the points that make up your endpoints. So I'm going to break this up into n subintervals, and each endpoint is going to be the same width away from the next one as it was from the previous one. So each subinterval, the way we're doing it, has a width of delta x equal to the total interval width, b minus a, divided by how many subintervals, which is just a very general n, which is 5 over n. So here's what the partition looks like here, and it's going to be kind of gross. My partition consists of the points. The first one's -2. The next one is -2 plus 5 over n. The next one is -2 plus another 5 over n, or I should say -2 plus 5 over n plus another 5 over n. The next one is -2 plus another 5 over n from the previous one. We just keep doing this until we get all the way to -2 plus n minus 1 times 5 over n, -2 plus n times 5 over n. Oh, that's just 3. So the partition is literally the set of all the points that breaks this interval up into however many pieces, in this case, n pieces. And the reason we get to say that the norm, so I should say, the norm of the partition is just the width of the widest subinterval. In this case, they're all the same width. So in this case, that's just going to be 5 over n. So here, when we say we want to find the limit as the norm width goes to 0, that's equivalent to saying the limit as n approaches infinity.
Is there a better one?
No, this is the best one. So but certainly, so right, we've broken this up in like this, right? x1, x2, x3, x4, etc., all the way to x sub n minus 1. So, right, so this is my x sub 0, and this is my x1, and this is my x2, this is my x3, all the way to my old second to last one and my last one. But the point, and I'll refer back to this handout that I gave you guys last time. Did I use it? Oh no. Yeah, this one here. Is that you could totally make a partition where things are not equally spaced out from each other. Or actually, no, this one is. Sorry, that's that. I thought it was, but these are all, we picked weird C's here. But you totally could make a partition where things were not equally spaced out. And then we need the requirement that the width of the widest piece, or the norm of your partition, gets smaller and smaller and smaller. Question?
So the partitions, are they defined in terms of the points on the x-axis or the width between each 2 points?
Partition, so the partition is defined in terms of points. So this set right here of points, this is the partition. That is the partition. And for the most part, we use a regular partition where each of the subintervals has the same width.
So when we say the norm goes to 0, we basically mean the difference between x1 minus x0, or x of n minus x of n minus 1.
Right, so it's all the same.
Okay.
Exactly. Now, let me look back here real quick. Yeah, where'd that example go? I'm always losing examples here, sorry. I had an example, I think I might have tossed it. That's too bad. Yeah, oh well. You can pick a different partition where things are not equally spaced out, as long as the widest one is still going closer and closer to 0. That's all we need. We need all the subintervals to get narrower so that our approximation isn't off by some large amount.
Doesn't that mean that you wouldn't be able to use the same delta x?
What do you mean exactly? Like,
Because like in this example, we're
Mhm.
using 5 over n.
right.
But if you have irregularly spaced
Uh-huh.
partitions, then could you still use that?
it becomes more challenging to do. It's certainly possible to try to calculate this sort of thing if you use an irregular partition. It becomes a much more difficult process to do.
Just use the longest one.
Well, that's what we're doing, yeah. But
If it was irregular, wouldn't the longest one be the most?
yeah, right. If you say that the length of the longest one has to get shorter and shorter and shorter, usually that condition also means the other ones have to get shorter as well. Again, I wouldn't get too caught up in this detail. I mean, it's good you're asking, but most of the time we are just like, we're going to use a regular partition. We're going to use right endpoints because it works and it's the most easiest way of doing it. So if we go back here, we were writing this out here. This is going to end up being, I kind of gave myself not enough space here. It's going to be the limit, then goes to infinity of, we're just taking our function and we're plugging in our x sub k, our right endpoint. So our x sub k, well, x sub 1 is -2 plus 5 over n, x sub 2 is -2 plus 2 times 5 over n. Oh, it's always going to be 1 to n for k. Okay. It's almost always, it's going to be 1 to n. K is going to go from 1 to n because we are looking at, right, here's my, like if your function looks like this, here's my first subinterval. And we're going to use the right endpoint to get a rectangle. And here's my second subinterval. We're going to use the right endpoint to get a rectangle. Here's my third subinterval, all the way to the very last subinterval, which is we're breaking this up into n pieces. So the idea is we're breaking this whole thing up into n pieces, using rectangles to approximate the areas of each of those pieces, and then each of those pieces is getting super duper narrow so that the approximation gets more close to being the right number. And of course I just wrote. So let me write the limit down here. We're gonna have the limit as n goes to infinity of the sum from k equals 1 to n of my function is 6x squared plus x, but I'm plugging in my x sub k. So it's going to be, instead of 6x squared plus x, it's going to be 6 times -2 plus k times 5 over n squared plus x, which is going to be my x sub k, which is -2 plus k times 5 over n. All times my delta x, which is 5 over n. Okay. So the rest of this is, well, I should say, the rest of this is a lot of terrible algebra and remembering some formulas. So let's look at the terrible algebra and remember the formulas. So let's see here. So we're going to multiply this out as quickly as possible. So we're going to say this is the limit, then goes to infinity of the sum from k equals 1 to n. All right, 6 times. So I've got to square this out. So I've got 6 times, let's see, 4 plus -2 times 5k over n is going to be -10k over n, but it's times 2, so it's -20k over n. And then 5k over n squared is going to be 25k squared over n squared. All of that still times 6 plus, well, this is just -2 plus 5k over n. All that times 5 over n. See, it's gross, but it's not undoable. It's just a little bit of bookkeeping. So now we keep going. The limit is n goes to infinity of the sum from k equals 1 to n. Let's see, I'm going to distribute my 6 here. So I'm going to do 24 minus 120k over n plus 6 times 25 is 150k squared over n squared minus 2 plus 5k over n. All times 5 over n. Keep going. We got the limit as n goes to infinity of the sum from k equals 1 to n. 24 minus 2 is 22, and 22 times 5 is 110 over n. I've got a minus 120k over n and a plus 5k over n, so that's a minus 115k over n. Times that 5 over n, which I'm not going to do in my head. And then finally, we've got the 150k squared over n squared times 5 over n. And I don't want to multiply those out. You know what? I don't have to. I can be smart about this. So I'm gonna break this apart now. I'm gonna break this apart as the limit then goes to infinity. I'm gonna have 3 sums. I'm gonna have the sum from k equals 1 to n of 110 over n. Minus, I'm going to pull out the constants, 115 times 5 over n squared times the sum from k equals 1 to n of k, plus 150 times 5 over n cubed times the sum from k equals 1 to n of k squared. Pulling out the constants. Yeah, I didn't want to multiply 115 times 5. It's totally fine. It's not that hard to multiply by 5, right? You can just multiply by 10 and divide by 2. That would work. That would be 1150 divided by 2, which would be 575, I think. It's not that bad, but I don't really need to. Now we use our formulas. Still writing the limit every time. So the sum from k equals 1 to n of a constant is just n times that constant. Last time I pulled out the constant, this time I didn't. Either way, you're just multiplying it by n. Here we're going to get 115 times 5 over n squared times n plus 1 over 2. Plus 150 times 5 over n cubed times n plus 1 times 2n plus 1 over 6. And now we can find the limit. N times 110 over n is just equal to 110. You don't even have to use a limit to get that part. But this part here, the leading coefficient on top is 5 times 115. And on the bottom is 2. Right? If you multiply this out, you'd have 575 times n squared plus some other stuff over 2n squared. Great. And then over here, let's see, well, on the bottom, we know we're going to have a 6n cubed. And on top, the coefficient of n cubed would be 150 times 5 times 2. Right? If you multiply that at the top, you get a 2n cubed plus some other stuff here. And if you multiply that by 5 times 150, you get 5 times 150 times 2. And then I guess we could simplify it. I don't really want to, it'll be good. Easy simplification, 2 and 6 cancel to give you a 3 there, and then 150 and 3 cancel to give you a 50 up here. So this works out to be not too terrible. 110 plus, okay, fine, 575 divided by 2 plus 5 times 50 is 250. So I end up with 360 plus 575 over 2, which is 720 over 2 plus 575 over 2. Which is 1295 over 2. Or if you like a decimal, 640, I don't know, whatever, 47.5. The numbers are not that important. The process is what's important. So I mean, yeah, I know I worked it out at the end here, but really this last like 2 lines, not that important. It's really getting from here to here and seeing that we can use these formulas and get this thing. Questions about what we've done here so far? It's kind of a lot, and I will remind you, just like I did last week, it's kind of a lot in the same way the limit definition of the derivative was kind of a lot at first. You might have done some really ugly derivatives using the limit definition, and then we learned a bunch of rules that made it a lot easier to do derivatives. That's going to be the same case here. This is the ugly definition we kind of have to get through before we then get to be like, oh yeah, but there's these nice rules that kind of work for all sorts of situations. Okay. What time have we got? Okay, we've got 20 minutes. All right, so yeah, let's do one more. Actually, let's talk about using the left endpoint instead of the right endpoint. Because you can totally use the left endpoint and it works almost the same. It's just not quite as nice. But let's do an easy one. Let's use left endpoints to calculate the area under y equals x from 0 to some arbitrary b.
I have a question from the last example.
Yeah, of course.
Okay. In one of the first few steps, when you were like distributed the square, when you're still doing the limit thing, you got
Like right here?
Yeah. Yeah, right there. How did you get the negative 20k over n?
Sure thing.
Yeah.
So I'm using kind of a very general formula that, so like right here, I'm thinking about this part here as a plus b squared, and it's equal to a squared plus 2ab plus b squared. So I'm thinking of
Oh,
my a
okay.
as -2, and -2 squared is 4, and my b is 5k over n, and b squared is 25k squared over n squared, and 2ab is 2 times -2 times 5k over n, which ends up being -20k over n.
And then is the k times 5 over n, is that the b because it's the endpoint, right? Or
Yeah,
okay, that makes sense. And then also in the end, did all the ends ended up canceling, right?
right. So I kind of, so I'll show the step, but usually I would encourage you to kind of skip right from this step to this step. But here's what I actually did. If I can write this in here, right? I actually kind of did the multiplying out. So I've really got the limit as n goes to infinity, n times 110 over n is just 110. Those do just cancel. But here what I've really got, 5 times 115 is 575. And we've got, sorry, minus, apologies, 575 times, this is n squared plus n over 2n squared. And here we've got plus 5 times 150 is 750 times, if I multiply this out, this is 2n cubed plus 3n squared plus n all over 6n cubed. So what I'm actually taking the limit of is the limit as n goes to infinity of 110 minus 575 n squared plus 575 n all over 2n squared plus 750 times 2 is 1500 n cubed plus 750 times 3 is 2250 n squared. Should pick smaller numbers. 750 n over 6n cubed. But now when we take the limit, well, the limit of 110 is 110. And this rational function that's a degree 2 polynomial on top and a degree 2 polynomial on the bottom, the limit of that rational function is the quotient of the leading coefficients.
Okay, yeah,
And
I
the
remember
same-
that.
And
Yeah.
the same deal over here. The limit of this third degree polynomial divided by this third degree polynomial is the quotient of the leading coefficients.
Oh, okay, I see. That makes sense. Thank you.
You're welcome. But, and I'll say this again, because I think it's important. I would encourage you never to write out all these steps, right? You should skip straight from, oh, I can see this to, okay, well, for this one here, I can see that the coefficient of n squared on top is 5 times 115, and the coefficient of n squared on the bottom is 2. And for this thing here, I can see that the coefficient of n squared on n cubed on top is going to be 150 times 5 times 2. And the bottom is obviously going to be 6. So I would definitely strongly encourage you to not do this work that I just showed you. In general, it's good to show it, to see it, but once you know it, you'd be like, yeah, I can skip that step.
I have another question.
Yeah.
When you're doing this, like, you already take out the 750 over n cubed times the summation notation of k squared.
Yes,
How do you go from the summation notation of k squared to,
that formula.
yeah?
So that's the thing one of the things we talked about on Friday, and those are formulas. You might have to memorize it, you might be given it, but we definitely have to be able to use it one way or the other. So they're on those handouts, but I'll just remind you, we definitely have the sum from k equals 1 to n of k is n times n plus 1 over 2. The sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. And what's really kind of fun, there's one more we usually are if you're expected to memorize these are the 3 you'll be expected to memorize. This one is just the first one squared, which I think is super cool. So yeah, you're typically, if you're expected to know them, these are the ones you're expected to know. There's a formula for the sum of k to the 4th, k to the 5th, so on and so on and so on forever, but you're not usually expected to know those. Someone could ask you to derive the one for the sum of k to the 4th. That's a question I've seen before, but not usually. But yeah, we're gonna do this. Cool. Let me, before you leave, Manny, let me give you this one handout. I think I sent you this one already, but it's fine. It's got something on the back. All right, so if we're gonna do this using left endpoints, same idea. We're taking our interval from 0 to b. Our partition is still regular, so we're just breaking this up into endpoints. I like to just call them x1, x2, x3, all the way to some x sub k minus 1, x sub k, all the way to b being x sub n. And I guess 0 is my x sub 0. So your lower endpoint is always your x sub 0, and your upper endpoint is always your x sub n. So my delta x here is just going to be b minus 0 divided by n, which is b over n. And my x sub, well, so I'm going to use the left endpoint this time. So my right endpoint, so the right endpoint of the kth subinterval. Well, here's my kth subinterval right here. The right endpoint is just x sub k, which is just 0 plus k times b over n, which is, I would write it as bk over n. But I'm going to use left endpoints instead. So instead of using x sub k, I'm going to use x sub k minus 1. So the left endpoint is going to be x sub k minus 1, which is 0 plus k minus 1 times b over n. Or if you prefer, b times k minus 1 over n. It's the same process. We're just using that endpoint instead of the right endpoint. So when I find my limit definition, from 0 to b of x dx, it's going to be the limit still as n goes to infinity, because my partition is regular. Right? It's the same as saying the norm of the partition goes to 0 of the sum from k equals 1 to n. But now instead of f of x sub k, it's going to be f of x sub k minus 1. It's my left endpoint. Still times delta x. It's always the same definition, essentially. It's always the function height times the rectangle width to get the area of the rectangle. And then, the limit as n goes to infinity of the sum from k equals 1 to n. Now, this one's particularly straightforward in that our function f of x, I know I draw my function curvy but really the function here is f of x equal to just x. Question? Or just stretching? Okay, cool. I don't want to miss a question. So here f of x sub k minus 1 is just my x sub k minus 1 times my delta x, which is b over n. Well, I guess I could have rewritten this, right? That's going to be the sum from k equals 1 to n. My x sub k minus 1 is b times k minus 1 over n times b over n. Now, I want to point out to all of you, look how much easier this would be if this was the right endpoint and it was b times k over n. If that was instead b times k over n times b over n, I would just pull out the b squared over n squared and have the sum of k, which would be way easier than what I'm about to do. It's still going to work to do what we're going to do, but it would have been easier to do it the other way. Also, I forgot the limit. Got to write the limit. Limit's important. Okay, so then more work this way. I'm still going to do that. Still going to pull out the b squared over n squared after I write the limit times the sum from k equals 1 to n of k minus 1. I guess I'll break that up into two summations. The limit as n goes to infinity of b squared over n squared times the sum from k equals 1 to n of k minus the sum from k equals 1 to n of 1. All that's times b squared over n squared. Then we use our formulas. So it's going to equal the limit as n goes to infinity of b squared over n squared times the sum from k equals 1 to k is n times n plus 1 over 2. And the sum of 1 is just n. Okay, I was worried it was going to come out wrong, but it's not. It's going to come out fine. So then I would distribute this through. Take the limit. This then goes to infinity of b squared over n squared times n times n plus 1 over 2. And my minus sign became a plus sign because I'm not paying close attention here, right? That minus, it's not going to matter because it's going to be 0, but it's important to get it right. That should be a minus sign. And then we have minus b squared over n squared times n is the limit of this. Well, the leading coefficient on top is b squared times n squared. I should say leading term. And the leading term on the bottom is 2n squared. So that's going to be b squared over 2. And here, if you have n b squared over n squared, that reduces to b squared over n. And as n goes to infinity, that's going to go to 0. Now, if you've ever seen the fundamental theorem of calculus, you know this is the right answer. You know that when you anti-differentiate x squared, you get x squared over 2. And then when you plug in b and you plug in 0, you get b squared over 2 minus 0 squared over 2, which is b squared over 2. I know I'm jumping ahead there, but just trying to make the connection to, if you've already seen this, it's the right answer. Right, yeah. So in fact, I have a handout as well. So do we have enough time? Maybe. Sure. So in fact, actually, let's do it this way. Let's be smart about this. So here's the handout I'm going to give you all. Not this. Maybe. Yeah, that one looks wrong for some reason. Maybe it's missing a page somehow. So this handout is 3 pages, and then there's some extra stuff on the back about like integral rules. So we will talk through this right now, and then on Friday we will talk about it more in depth. Well, and for those of you on Zoom, I'll post these handouts on Canvas, or you can also find them on Dr. Kuba's website. Well, let's go ahead and take a look at this here. So there are 2 parts of the fundamental theorem of calculus. The part we care about and the part we don't. That's not entirely true, but it's kind of true. So let's take a look here. We have, and so let's read through this. This is Dr. Kuba's handout. It's pretty great. Making the connection between area and antiderivative. So we're going to assume that our function f of x is positive because it makes it easier, but you don't have to have that. And we're going to say that the integral from a to b of f of x dx is just the area under the curve from a to b, or the area of the shaded region. Then we're going to define something. We're going to make a new definition. We're going to say, okay, well, I want to say that this function, capital F of x, so named because it's right. We're trying to be very kind of leading here with this, right? It's kind of the obvious name. We're going to say that's the area under this curve from a to x. So this area right here, this area is capital F of x, is all this shaded area. As x gets bigger, f of x gets bigger. As x gets smaller, f of x gets smaller in this particular example. And it's totally correct to write that capital F of x is equal to the integral from a to x of f of t dt. We had to call it a new name because we're using x here. So we called this function, instead of calling it y equals f of x and saying this is x and this is y, we called it y equals f of t. And so this is the t-axis and this is y. Same thing. A couple things to observe. Thing one, if you plug in b, capital F of b is just going to be the integral from a to b. Right? We're just plugging in b for x, which is the area. So capital F of b is all this area under the curve. And capital F of a is the area under the curve starting at a and ending at a. Well, that's going to be nothing. If you start and end at the same spot, you've got no area. Always true. So then, looking at the next page, here's where things get a little kind of crazy. We want to find the derivative of capital F of x. Okay, well, we're going to appeal to the limit definition of the derivative. So using the limit definition, the derivative of capital F is just the limit as h goes to 0 of capital F of x plus h minus capital F of x, all divided by h. Usual definition, right? From 21a. But then if we think about that, well, here's capital F of x, this blank area here, right? This is capital F of X, all this right there. And capital F of X plus H is everything from here to there. And so the difference between them is the area of this thin strip from X to X plus H. Stop me if you have questions. I'm pausing for just a second to see, like, just make sure like people are cool with what I'm saying. Okay, so all we're saying is that this F of X plus H minus F of X is just this area here. That's what that is on top. Cool. Now here's where things are a little dicey, but not that dicey. There's the mean value theorem for integrals, which is really just the same as the mean value theorem. We just write it in terms of intervals. Here's what it says. So you guys remember the mean value theorem? Maybe it says that if you've got a function that's continuous on an interval, that somewhere in the middle of the interval, the derivative is equal to the slope of the tangent line, or the slope of the secant line. Sorry, slope of the line. So, okay. So here's what we're going to say. Okay, so this is how much time? Okay. So basically, the idea here is that there's got to be a point where the area of f of c times h, so this thin strip, there's got to be some point in between x and x plus h where the height at that point times the base is equal to the area there. I'm going to say that again. So basically, we're just saying there's got to be some point c between x and x plus h where the area of this rectangle is equal to the area of the shaded region in black. Because if you pick the lowest point and the highest point, you're going to get somewhere in between the actual value, right? This black area is definitely more than this area here. And this black area is definitely less than this area here. And since we hit every height between this lowest point and this highest point, there's got to be some point in between these two where the height is right, and that height times this base equals the area of the black shaded part that's curvy. But here's what that means for us. It means that there's some point C where f of c times the base, which is h, is equal to this here. We can talk about this part specifically more next time, but I want to move on to the last part just to kind of get to there. So here's what that means. It means that this area of the thin strip really is f of c times h. There is some c between x and x plus h, where that area here is really just f of c times h. Then the h's cancel. And now check this out. If we take the we take the limit as h goes to 0 of f of c, well, look where c lives. C lives between x and x plus h. So if h is going to 0, that means this point here is going over to that point there, and c is going to get smashed over to x because it has nowhere else to go. If c is between x and x plus h, and x plus h is getting closer and closer to x because h is going to 0, then that c is getting closer and closer to x. So this ends up equaling f of x. And that is the real gist of the fundamental theorem of calculus, that the derivative, capital F prime here, the derivative of this integral is equal to f of x. Or in other words, when you do the derivative of the antiderivative, you get back the function that you started with, which shouldn't be surprising, right? You're kind of like, what's the big deal about this fundamental theorem of calculus? We're saying some real basic stuff here, but it's really important. And so that is, let's see, where's page 3 here? Yeah, so that is the gist, that the derivative of f of x, capital F of x, is equal to little f of x. Or in other words, and I don't love this notation that he's used here, but whatever, the derivative, capital D, of the integral from a to x of f of t dt is equal to f of x. I'll leave you with that. We'll definitely talk about this more on Friday. 2 is not, so 2 is the thing you actually want. The second part of fundamental theorem of calculus is the part that tells you if you take the antiderivative and then plug in the endpoints, that gives you the area. Okay. So this fundamental theorem of calculus part 2 is the more used part in this class. It's derived from part 1. But part 1 is really the most, I know it seems kind of basic like this, But this theorem is the whole basis for what we do, that the derivative and the antiderivative undo each other.
D is supposed to be like.
This means
D-
derivative.
D steps, right?
Yeah. I would never write this.
Yeah,
I would
no,
write,
that-
I would write d dx of the integral from
Yeah.
A. Yeah, I know I debated, should I use this? Yeah, but yeah, I don't love that notation.
Thank you.
You are welcome.